Hello everyone and welcome to our first lesson in Chapter 16, Thermodynamics. So in your OneNote in Chapter 16, Thermodynamics, I'm going to be starting with the very first slide in your notes. So we're going to be talking mainly about temperature and heat and how heat moves and in general how those properties work, and then we will also be doing some calculations as well. So first thing, what is temperature and heat? Are they the same thing? And what causes heat? So in terms of temperature and heat, they are not the same thing, and I'll explain more of that on the next slide. But in general, what causes heat is molecules moving faster. So in order to make molecules move faster, you have to put energy into them. So for instance, when you cook something, that flame, that fire, is essentially energy, and that is heating up, in this case, the water molecules, causing them to move faster, and that's what causes heat. You can also get heat from friction. So if you're drilling something, the drill is moving very fast, causing friction. That can also cause heat as well. So let's talk about the differences between temperature and heat. So temperature is how we measure how much thermal energy something has. Now, thermal energy, this is essentially the same thing as saying heat. It's just a little bit more of the proper term. There are many different types of energy. There's electrical energy, there's chemical energy if we're talking on the molecular level in bonds, and there's thermal energy. There's many different ways that energy comes in terms of forms. And today we're going to be talking about thermal energy, which is heat. So temperature is how we measure heat or how much thermal energy something has. So let's talk more about just general concepts and properties in relation to that. So if two objects are in contact with one another long enough, the two objects will have the same temperature. So this helps us to also further define temperature. And when two objects have the same amount of thermal energy, they will be at the same temperature. So again, equivalating temperature with a way of measuring thermal energy or heat. So when the physical properties are no longer changing, the objects are said to be in thermal equilibrium, meaning both objects contain the same amount of heat or thermal energy and therefore have the same temperature. So two or more objects in thermal equilibrium have the same temperature. So this is the 0th law of thermodynamics, and when you guys take physics next year, you will learn a little bit more about thermodynamics in general. Now again, going to this topic of two different objects being at the same temperature, here's a way to visualize that. So when two objects at different temperatures are placed in contact with one another, that direct contact, that's an example of conduction. We'll actually talk about that more later. Heat is going to flow from the object with the higher temperature, and therefore the one that has more heat or thermal energy, to the object with the lower temperature or thermal energy. So heat added increases temperature. We know that, and heat removed, I'm going to highlight this, decreases temperature. Now, this is a really important concept. I like to say that there's no such thing as cold. Cold is simply just the lack of heat. So when something is cold, that means that heat is leaving it, okay? It's not like something is becoming cold and gaining more cold. It's the absence of heat. So heat and temperature, as we said, are not the same. Temperature is a quality that tells us which direction heat will flow, and it also tells us like how much heat that we are dealing with. So in this picture, for example, we have two objects, the red square and the blue square. Now the red square has a higher, the T stands for temperature, than the blue square. Therefore, it has more thermal energy. That's what that Q is representing, and we'll talk more about this equation later and what that means. And this has more heat, and therefore this heat is going to flow towards the object with less heat or has a lower temperature. And over time, once they've reached the same temperature, so eventually their temperatures will be equal, that is when we will be in equilibrium, okay? Or thermal equilibrium, and they'll be at the same temperature. So here's an example. So this is very abstract. Let's talk about some actual real world examples. So again, what happens when objects, and again, we could be talking about physical objects like we were here, like solid objects, or you can actually discuss this in terms of fluids, so something that's a liquid as well, that are at different temperatures come in contact with one another. So again, the colder object will get warmer because heat's going to move from the warmer object to the colder object, from the thing that has a higher temperature to a lower temperature, until they both reach the same temperature. So what is this that flows between the objects? So what is it that flows between the objects to account for this? So again, we're going to use that term heat for that quantity. So for example, you have a hot cup of coffee, right? This definitely has a much higher temperature than the cold milk, okay? This definitely has a lower temperature. So when you add the milk to the coffee, what's going to happen is the heat from the coffee is going to move towards and into that milk, and it's going to cause, we'll say this is milk, and that's going to cause the milk to become warmer, and it's going to cause the coffee to become colder because the heat is leaving the coffee and going into the milk. So that is how your coffee gets cooled down. It's the same thing with ice and ice cubes. So if you have a glass of water, the water is obviously warmer than the ice cubes and has a higher temperature. So when you put ice cubes into a cup of water, the energy from the water, it has higher temperature, higher energy, higher heat, is going to flow into the ice cubes. It's causing the water to decrease in temperature. The ice will gain that heat and, of course, start to melt then. So in general, that's how a lot of everyday those are some everyday examples where heat is moving and flowing from a warmer object to a colder object until, of course, they both reach that thermal equilibrium. So those are some everyday examples. Now let's talk about specific heat. So we have a new term that we're going to introduce, specific heat capacity. Oftentimes it's going to be represented with this C here. In the lab that you're going to do later, you'll see it represented CP. But in general, we're going to see it represented as C, okay? Now, heat flow is a form of energy transfer between objects. That's what we were just talking about. Now, to be more specific in this example, so let's say we have 100 grams of water at room temperature, okay, in both of these, all right? Both of these have the same amount of water. They're both at room temperature. All right. Now, if we're going to add 100 grams of room temperature steel into these two are going to be hot water, okay? So let's say both of these are hot, okay? Not room temperature. So these are both hot, okay? And let's say we add room temperature water and room temperature steel to both of those. Which one do you think is going to cool down the water faster? This one is actually going to cool down the water much more quickly than the steel. And the reason for that is the steel has what we call a lower specific heat capacity compared to water. And specific heat capacity of a material is the relative amount of heat needed to raise its temperature. So water has one of the highest specific heat capacities, meaning it takes a lot to change its temperature. So since we're adding this room temperature water and it has a very high specific heat capacity, it's going to be able to absorb more of the energy and more of the heat from the hot water than the steel will. And I'm going to illustrate this. This will be a little bit more clearly illustrated in this FET right here. So I'm going to click this button. This tells us how much energy each of these things can absorb, and energy, of course, being our heat. So you can notice right off the bat, the water has a lot more ease in it because it has a much higher specific heat capacity. So what I'm going to do is I'm going to take the iron. I'm going to put my little temperature here. Okay, so notice the water, very low temperature to start. And I'm going to heat up this iron. So notice it's gaining energy because it's getting warmer. All right. And I'm going to put this into the water. Okay. And I'm going to see how much it's going to change the temperature of the water. Okay. So this is pretty warm. So I'm going to put this in the water. Okay. So we increased, all right, to about this 1, 2, 3, 4th line right here. Okay. So now I'm going to do the same thing. I'm going to grab a new thermometer here. I'm going to do the same thing with the oil. And again, I said the water has a much higher specific heat capacity. So we're going to see when we heat up this iron, in which of these liquids are we going to see the most change? So in the water, we saw it went up to about that 4th line. So now I'm going to do the same thing with the oil. Okay, so notice that we increase the temperature a lot more, okay? And the reason for that is water has a much higher specific heat capacity. So it takes a lot more heat and energy to change the temperature of this water, okay? Versus the oil, you saw it went up a lot more. It was a lot easier to change its temperature because it has a lower specific heat capacity. And here's the formal definition of that. So specific heat of a material is the quantity of heat needed to change a unit of mass of material by a unit amount in temperature. So to be more specific, for example, to change 1 gram by 1 degree Celsius. So oftentimes, this is what we're looking at, grams in degrees Celsius, because that's what we use in science, okay? So how much heat is needed to change the temperature of a material by 1 degree Celsius if we have 1 gram of that substance, okay? Or per gram of that substance. Now, oftentimes you're going to see a specific heat with this unit right here, calories per gram degree Celsius, but instead of calorie, you might also see joules as well. And for water, if we're talking about calories per gram degree Celsius, again, calories and joules, this is a way that we're measuring heat. The specific heat of water is 1 calorie, per gram degree Celsius. So it takes 1 calorie, which is a measurement of heat, to raise the temperature of 1 gram of water by 1 degree Celsius. Now, how can we put that into numbers? So we have this equation right here, Q equals M times C times delta T. So oftentimes I'll say MCAT just for short. So Q is going to be the amount of heat in joules. Sometimes you might again see calories as well. M is of course going to be our mass, which is specifically in grams. And C is going to be the specific heat capacity that I talked about. Again, we might see calories, but for the most part, we're going to use joules. And this delta T, is the change in temperature. And in the next video, we'll go over some mathematical examples with this.